Welcome. In this session we will look into general algebraic modeling system GAMS. So, previously we had seen that there is no inbuilt function in MATLAB which can solve MINLP problem, a mixed integer nonlinear programming problem which has equality constraints, but GAMS can also solve problems which are nonlinear as well as they can have equality inequality constraints, and some of the variables or all of the variables can be integer. GAMS is a high level modeling system for mathematical programming. It has been designed for modeling optimization problem. So, here if we see, we have GAMS over here, right, and then we have solvers over here, right. So, in this session we will be looking into only GAMS, right. Depending upon the license, GAMS can access the solvers. So, as you can see here, GAMS is a modeling platform, right. So, this modeling platform helps us to write the models which are similar to the algebraic equations which we would develop using pen and paper, and then it has variety of solvers, right. So, for example, here we have shown solvers for linear programming, mixed integer linear programming, nonlinear programming and mixed integer nonlinear programming. So, all of these solvers can be used to solve a linear programming problem, right. So, similarly for MILP we can use Simplex, Gurobi, Mosaic, Express. For nonlinear programming we have CONOPT, IPOPT-H, K-Nitro, MINOS and SNOPT. Similarly, we have for mixed integer nonlinear programming Baron, Alpha ECP, DICOPT and other solvers, right. So, when we are to purchase GAMS, there is a cost involved for getting the modeling platform GAMS, and depending upon the set of solvers which we choose, we will have to pay to get those solvers. Some of these solvers may be available free of cost. For example, Gurobi is available free of cost. So, the models which we write in GAMS would be compatible across platforms. So, a code which has been developed on Windows would also run in Linux, provided we have GAMS on both of them, right. So, GAMS is used in more than 120 countries, and further details about GAMS can be found on their website. So, this table shows the various solvers. So, these are the solvers, the rows are the name of the solvers and the columns are the types of problem, right. So, in GAMS, mixed integer linear programming is actually called as mixed integer programming, right. So, MIP actually indicates what we have been using as MILP. So, LP, MIP, NLP and MINLP. There are various other classes of problems, you can look into that. So, now if we look at this Gurobi version 9, it can solve linear programming, it can solve mixed integer linear programming and it can solve QCP quadratic programming and mixed integer constraint quadratic programming. So, if we look into Baron, it can solve LP, MIP, NLP as well as MINLP, and it also solves various other classes of optimization problems. If we are to solve a mixed integer nonlinear programming problem, then it is not sufficient to just have GAMS. We also need to have an appropriate solver which can solve mixed integer nonlinear programming problems. So, you can download the demo version of GAMS from their website, right. So, here you can download it for Windows, Linux, Mac, and for other platforms you will have to fill a form to request the corresponding version, right. So, without license, if we execute a GAMS file, we would get an error, right. So, this is the error which we would get if we execute GAMS file without having the appropriate license. With the demo version, we can solve linear models, right. So, when we say linear models, it is linear programming, mixed integer programming or MILP. So, remember, as we discussed earlier, mixed integer linear programming is termed as MIP in GAMS, and this is relaxed mixed integer programming problems. So, for linear models, it can support up to 2000 constraints and 2000 variables. For all other model types, it can support only 1000 constraints and 1000 variables with a demo license. So, this demo license can be obtained without any cost, right. So, we just need to fill a basic details over here and we would get a license file to the email address which we provide here, that can be used to install GAMS on your system. So, when you install GAMS on your system, you will get two options. One is IDE option and another one is GAMS Studio option. So, for the rest of the discussion in this course, we will be working with IDE option. You can also install Studio option and look at GAMS help which is available to continue using the Studio version. So, the bottleneck which we have over here that can solve only problems of a specified number of variables and constraints can be overcome using NEOS. So, NEOS stands for Network Enabled Optimization System, right. So, this is the website for NEOS server. Once we code our problem using GAMS, right. Then we can submit our job to NEOS, right. So this is an online solver, and we'll have to select the type of problem which we have, and if we submit our job online, we can get the results over email, or it is displayed after the completion of the problem. So NEOS not only supports GAMS file, but it also supports various other types of input. So for example, if we take this solver SCIP, then we can also input a AMPL file, a Ciplex file. We can also give the input in terms of GAMS, as in terms of MPS, in terms of OSIL. We can also give Python input and ZIMPL input. So we will restrict our discussion to GAMS input. Right. So for example, in MILP, we can give an AMPL input, a GAMS input, a Mosel input, as well as an NL input and MPS input. So these are various modeling platform, or it is a type of file that can be given as input if we select MILP solver in NEOS. So you can visit the website of NEOS to see the list of solvers that they support. Currently they support more than 60 state of the art solvers. Right. So the contributing universities for NEOS include University of Wisconsin in Madison, Arizona State University, and University of Klagenfurt in Austria, and the University of Minho in Portugal. So this is the GAMS interface, right. So over here we have this model libraries. In model libraries, you will be able to find a lot of problems, right. So for example, let's click on this GAMS model library. Right. So over here we have name of the problem, right, and the application area. So for example, this problem ABEL is from macroeconomics, and the type of problem is a nonlinear programming problem, so NLP. This column shows the name of the contributor, and the last column gives a brief description about the problem. So here it is a linear quadratic control problem, right. So you get some information about the problem over here as well, right. So you can click on any of these columns, right, to arrange according to that column. Right. So for example, if we click on this application area, so all the problems are listed in alphabetical order. We have applied general equilibrium, chemical engineering problem, disjunctive problems, problems from energy economics, then we have engineering problems, finance problem, and these problems basically show some of the advanced features of GAMS language. Right. So these are set of problems which are from management science and operation research. Right. So these are some problems from mathematics, and then we have microeconomics, statistics, and stochastic programming, right. So we can also arrange the problem according to its type, right. So these are the various types of optimization problem. So here we have linear programming problem LP, we have mixed integer nonlinear programming problem MINLP, right. So in GAMS they do not use the term MILP, right. So they do not use mixed integer linear programming, but they use the term mixed integer programming, right. So what we have been discussing as MILP, in GAMS terminology they use MIP. So over here we have that traveling salesman problem which we had discussed in the introductory lecture, right. So this is a problem related to investment planning in the Korean oil petro industry. This problem is a mixed integer linear programming problem and deals with portfolio optimization for electric utilities, right. So these are examples of nonlinear programming problems. This is the Rosenberg function which we had discussed previously. So you can also sort them according to the description. So for any of this problem, if we double click it, right, so it will open the file. One of the interesting feature about these examples is that it also gives us the source of the problem, right. So typically it is a book or it is a journal paper, right. So whatever problem is discussed over here actually comes from this work, right, which was published in European Journal of Operational Research. So not only we get a code, but also we get a source wherein the description of the problem is given. So now we have the problem description as well as code, right. So if we are interested in this particular problem and we want to solve it with a different set of values, so we can change the values and still execute this problem to get the results without putting in additional effort to actually code the problem. These are model library. So there are some special model libraries also. This model entirely deals with power system optimization modeling, right. So from the book by the author Sorodi. So over here the name of the chapter is given, the model name is given, and also a brief description is given. So for example, this problem is a multi-objective economic environmental load dispatch, right. So if you double click on that, we can again have access to the file, right, and the description about this problem can be obtained from this particular source. We also have a package on nonlinear optimization applications, right, by Andrei. So, over here you will be able to find examples for a lot of nonlinear programming problems, right. So, for example, here we have a 3 bar truss design problem, here it is a 4 bar truss designing problem, designing of a flywheel and so on. So, we can also change the default solvers in file, we can go and select for this options, right. So, when we select this options, a lot of things can be changed, right. For example, the font size in GAMS editor file, we expect you to explore all of this, right. So, we will only talk about this solvers. So, in solvers over here you will be able to find the name of the solver. So, this alpha, ECP, AMPL, Antigone, Baron, BDMLP, all these are names of different solvers, right. So, not all solvers are capable of solving every type of problem. So, over here alpha ECP can be used to solve MINLP problems and MIQCP problems, right. So, if we look at these solvers, right. So, we have Ciplex over here, right. So, Ciplex currently it is in demo license, right. So, it can solve linear programming problem, it can solve mixed integer programming problem, it can solve MIQCP, it can solve QCP, it can solve RMIP, it can solve RMIQCP, right. For linear programming, if we want to select, let us say Baron solver, right. So, we need to click over here. So, now whenever we solve a linear programming problem, it will use Baron to solve this unless we override the options in the GAMS file itself, right. So, similarly we can select Baron for solving MINLP problem. Right now BONMIN is being used, right, but if we want to override that option, we can click over here, right. So, now linear programming as well as nonlinear programming will be solved by Baron, right. So, we can reset this to the default values. So, clicking on a particular solver name will make it the default solver for the compatible set of problems, right. So, for example, if we click on CONOPT, then all these dots would become X, right, but if we click on this particular dot, right, then only for linear programming problem Ciplex would be used, right. So, for rest of the problems still CONOPT 4 would be used. So, you can also look at this help, right. So, over here you will find the online help as well as the offline help of GAMS documentation. You can also look into this expanded GAMS guide by McCarroll. So, over here you will also be able to find some of the advanced features of GAMS. The example that we are going to discuss is from the offline documentation. So, this is the offline documentation which is available. In the tutorials and examples, we look into this tutorial by Richard Rosenthal. So, as and when you start using GAMS, you will require a lot of different features, right. Detailed help is available over here. So, you can look into the appropriate section of the help. So, now we will look into the structure of the input and output in GAMS, right. So, the various components in input are sets, data, variables, equation, model and solve statements, and then we can have display statements. So, the display statement is optional, right. So, for sets, data which can be in terms of parameters, tables or scalars, and in variables, right, we need to first declare it and then assign values and members to it. Similarly, for equations, we need to first declare what are the equations and then define the equation. We will use model and solve statements to build a model and then to subsequently solve it. Display statement can be used to display the results in a specified format. By default, GAMS displays a large number of output, but if we want to display a specific output, we can use this display statements. For variables, we can also specify the bounds and the initial values. So, it is not mandatory, but if we have an initial starting point, then that can be provided to GAMS, right. Similarly, if we have bounds, that can also be given. So, these are the components of input. For output, we will get something known as a list file and a log file. So, a list file will have echo prints, which is nothing but the reproduction of the model. We will have reference maps, equation listings, status report and solution report. So, when we have a list file, we will look into each of them. There are two playlists which are available in GAMS channel. One is an introductory series which has 3 lectures and the other one contains advanced features of GAMS, right. The links are provided over here. So, we will take this small example, a linear programming example, and we will model this problem and we will see how to code it in GAMS, right. So, these are 3 marketplaces, New York, Chicago and Topeka, and there are 2 plants, one in Seattle, one in San Diego, right. So, the demand for a product in New York is 325, in Chicago it is 300 and in Topeka it is 275. The number of cases which the plant in Seattle can ship is 350 and the number of cases which the plant in San Diego can shift is 600. right. So, these values are the distances between the plant and the market in thousands of miles. So, the optimization problem is that we need to satisfy the demand at these three places at New York, Chicago and Topeka by shipping either from Seattle or San Diego. So, the optimization problem is to ship cases from the plants to the market such that the demand is satisfied at all the three markets, right, and the supply constraint is not violated, and the total cost involved in transportation should be minimum. So, the freight cost is given and the distance is known, right. So, we need to satisfy the demands at these three markets without violating the supply constraint and minimize the cost. That is the optimization problem over here. Let us use the notation Dij to denote the distance, right. Let us use the notation I for the plants and j for markets, right. So, distance between a plant and market would be indicated by Dij. So, D11 can be the distance between Seattle and New York, which is 2.5. F is the freight in dollars per case per 1000 miles, which is given as 90. Ai is the supply of commodity at plant I, right. So, A1 is 350 and A2 is 600, right, because that is the maximum number of cases which can be shipped from Seattle and San Diego respectively. So, this is Bj, right. So, Bj is the demand for the commodity at market j, right. So, B of 1 is 325, B of 2 is 300 and B of 3 is 275. So, the cost for shipment is given by this expression, that the cost of shipping from ith plant to the jth market is F into Dij by 1000, right. So, F is given as 90 in this case, Dij is given over here, the distances are known. So, divided by 1000 will give us Cij, right. So, in this case we will have to first select the decision variables, right. So, decision variable can be Xij. So, Xij indicates how much quantity is supplied from one plant to one particular market, right. So, the decision variables are how much is transported from Seattle to New York, how much is transported from Seattle to Chicago, how much is transported from Seattle to Topeka, and how much is transported from San Diego to New York, how much is to be transported from San Diego to Chicago, how much is transferred from San Diego to Topeka, right. These are the 6 decision variables that we have, right. So, that we indicate by Xij. I is for the plants and j is for the markets. So, this expression gives us the total cost. So, what we are saying is the cost of transporting from Seattle to New York into the quantity that is transferred from Seattle to New York plus the cost for transporting from Seattle to Chicago into the amount that is transported from Seattle to Chicago, and similarly the other terms, right. So, we will have 6 terms. So, instead of writing this expression, we can compactly write it as sigma I equal to 1 to 2, right. So, this is for the plants and then this is for the cities, right, for j is equal to 1 to 3, right. So, if we basically expand this, it will be C11 x11 C12 plus C12 x12 plus C13 x13 plus C21 x21 plus C22 x22 plus C23 into x23, right. So, instead of writing this 6 terms, we can compactly write it like this. So, no matter how many cities and markets are involved, this expression would remain the same. We just need to change instead of this 2 and 3 with the respective number of markets and plants. So, now we have this objective function. So, this has to be minimized. So, now let us look at the constraints, right. So, here we have 2 types of constraint, that whatever is shipped from Seattle, right, should be less than or equal to 350. Remember, the constraint is not that we need to ship 350 from Seattle, the constraint is that we can ship a maximum of 350 cases from Seattle, right. So, what is getting shipped from Seattle to New York is X11, what is getting shipped from Seattle to Chicago is X12, and what is getting shipped from Seattle to Topeka is X13, right. So, this is what is required from Seattle. So, this has to be less than equal to 350. So, that is what is compactly written over here, summation over j, right, for each plants. So, that is what is written for each plant, right. So, the plant in Seattle, so this is I is equal to 1 and this is I is equal to 2. So, for each plant we are writing one constraint, right. So, the first constraint is summation j is equal to 1 to 3 x 1 j is less than equal to A1. So, A1 in this case is 350. So, basically what we get is what we have over here, right. Similarly, the second constraint would be summation j is equal to 1 to 3 x 2 of j is less than equal to A2. So, the second constraint would be x 2 1 plus x 2 2 plus x 2 3 would be less than equal to A2, right. A2 in this case is 600, right. So, these are the two supply constraints, right. So, we can compactly write it using this expression. Again, let us say if there are 10 plants and let us say 20 markets. So, this will just become j is equal to 1 to 20 xij is less than equal to ai for I belongs to 1 to all the way up to 10. So, now that we have taken care about the supply constraint, we also have another constraint which says that the demand in New York is 325, the demand in Chicago is 300 and the demand in Topeka is 275, right. So, again we need to remember that it is not exactly 325 cases are required, it is at least 325 cases are required. So, we can supply more than 325, but not less than 325. So, in this case for New York we need to write a constraint, for Chicago we need to write a constraint, for Topeka we need to write a constraint. So, that is why we have for all j belongs to 1, 2 and 3, right. So, we will write a constraint for New York, for Chicago and for Topeka, right. So, the amount that is coming from Seattle to New York plus the amount that is coming from San Diego to New York. So, this is the total amount of quantity which is coming to New York. This should be greater than or equal to 325. Right. So, that is what has been written by this constraint. For New York it is x11 plus x21, right, summation over I should be greater than or equal to 325. Similarly, we have x12 plus x22, right. So, this is the balance over Chicago. So, this has to be greater than 300. Similarly, we have x13 plus x23 should be greater than or equal to 275. Right. So, these three constraints can be compactly written using this one expression, right. And since xij is the number of cases which are transported from a plant to a market, it has to be greater than or equal to 0, right. So, it is not necessary that every plant ships to a particular city. So, as long as these constraints are respected, any number of cases can go from any particular plant to any particular market. So, now we have this model over here, that model is written over here. So, this is the model we have. In addition to this, we have xij is greater than or equal to 0. So, the discussion that what we are going to have here is also available here as part of GAMS help, right. So, you can also look at that discussion. So, first we will identify the number of sets which are present in this problem. So, in this case there are 2 sets which are available, right. So, we use this keyword sets to define 2 sets. The name of the first set is I, the name of the second set is j, right. So, I and j are the 2 sets which we are using. So, I we are going to use it for denoting the plants and j we are going to denote it for markets. So, the name of the set is I and j. So, we need to give 2 values for I because we have 2 plants, one in Seattle and another one is San Diego. Similarly, we have 3 markets, New York, Chicago and Topeka, right. So, these are the values over here. So, once we are done with defining sets, we need to provide this semicolon, right, and the values are to be given within this slash operator. So, starting and ending, right. So, New York, if you remember, we had space in New York, right. So, spaces are not allowed over here. So, we have used New hyphen York. So, we have first defined sets, right, we have declared what are the sets. So, we have 2 sets I and j and then we have assigned the values for those sets, right. Now, we will provide the data whatever we have, right. In GAMS data can be in terms of parameters, tables or scalars, right. So, parameters is usually used for vectors, right. Table is for usually providing data in the form of a matrix and scalars are constant single values, right. If you recollect the problem, you would know that we had constraints on Seattle and San Diego as to how many cases it can transport, right. So, here what we are doing is we are defining a parameter A, it runs over the set I, right. So, set I means A of Seattle and A of San Diego, right. So, what we have over here Seattle and San Diego should come over here Seattle and San Diego, right. This scanning plants, this market is more like a description. We can give any values and it can also have spaces, right. So, for example, here we are saying A is capacity of plant I in cases, right, and again within this slash operator we provide the values, right. For Seattle it is 350, so we write Seattle because Seattle and San Diego are the elements of I. So, we are saying A of Seattle is 350, A of San Diego is 600. Similarly, we use another parameter B, right. This parameter is for every element in the set J, right. So, in this case J is nothing but the markets. So, we have 3 markets, New York, Chicago and Topeka, right, and these are the elements of this set J, New York, Chicago and Topeka. So, we write New York, Chicago, Topeka and the appropriate values which we have 325, 300 and 275. So, once all the parameters which are required are defined, we need to end it with a semicolon over here. So, in MATLAB you would put semicolon in every line, and even if you do not put semicolon you would not get an error, it will just print things in the command window also. Over here you need to compulsorily put a semicolon, right. So, we have defined 2 sets, we have given the parameters with respect to the markets and the plants, right. Now, we need to provide the distance. So, the distance if you see it is in the form of a table, right. So, we use this keyword table. So, sets, parameters and tables are keywords. So, the name of the variable is D, right, and D is I comma j. So, the rows indicate the plants and columns j indicate market, right. So, we have 2 plants which are the rows. So, here we have in rows Seattle and San Diego, and we have 3 columns New York, Chicago and Topeka. So, here it is New York, Chicago, Topeka. These are the elements of the set. So, GAMS understands that I, when we refer to I, we are referring to this ith set I, and set I contains 2 values Seattle and San Diego. So, it expects 2 rows over here. Similarly, for markets we refer it using J, right. So, and there are 3 markets, so 3 columns. The columns should be New York, Chicago and Topeka, right. So, these are the values which are given to us. So, we directly write those values, and once we are done defining table we need to again end it with a semicolon, right. So, we have seen sets, parameters and table. So, we can also provide data in terms of scalar, right. So, scalar is a keyword, right. Over here we are defining a scalar f. So, the description of f is freight in dollars per case per 1000 miles, right. So, this is a description and the value is again entered between these 2 slashes. So, the value in this case is 90. So, once we are done defining scalars we again need to end it with a semicolon, right. So, now we have to calculate this Cij, right. Remember the expression Cij, Cij is equal to f into Dij by 1000, right. So, we have defined this Dij, we have defined f, and this is 1000 is a constant value. So, now we need to calculate this Cij. Remember, this is not a constraint, right, because this does not have any decision variable. Dij is known, f is known, 1000 is known, Cij can be uniquely calculated, right. So, that is what we are going to do now. We are defining a parameter C, it runs over the set I comma j. This is the explanation for Cij, and here we write the expression for calculating Cij. So, C of I comma j is equal to f, which is a scalar which has been defined, into D of I comma j, which is also defined, divided by 1000, and we put a semicolon, right. So, whatever preliminary calculations are required can be written over here itself. So, now we have defined all the data which is required for this problem, right. So, now we will define what are the variables that are required. Here we have 2 types of variables. So, variables again is a keyword. So, we have variable x and z, right. So, z will indicate to denote the objective function, right. So, objective function is also considered as an equation in GAMS, right. So, if it is an equation we need to have a left hand side to this. So, instead of minimize summation Cij xij, I is equal to 1 to 2 and j is equal to 1 to 3. What we are doing is we are saying minimize z, right, subject to whatever the rest of the constraints are, right, and in addition we also have this equation which says z is equal to summation over I and summation over j xij Cij. So, that is why we have this variable, right. So, this variable z will indicate the total transportation cost in thousands of dollars, right. So, that is the purpose of this variable z. This xij is the decision variable which we discussed earlier, right. So, x of I comma j. So, once we write I comma j, GAMS understands that I which we have defined is a set. So, it has the values of Seattle and San Diego, and J, which we have previously defined as a market, has the values of New York, Chicago and Topeka. So, this is how we define the variables. Since we have this requirement, we write positive variables x, right. So, positive variable, this is again keyword, right. So, it indicates to GAMS that x can take only values which are greater than or equal to 0. So, we do not have an upper bound on x, right. So, that is why we do not need to give over here, and then we have 3 equations over here. So, this is the equation for supply, this is the equation for demand, right. So, let us call this as equation for the total cost, right. We have 3 equations, we need to first define the name of the equations and then define the equations, right. So, here we use the keyword equations and write cost, supply of I, demand of j, and write whatever description that we want for each of them, right. So, now GAMS will be able to interpret that cost is just one equation because there is no indexing, supply is for every element in set I. So, set I contains 2 values, Seattle and San Diego. So, when we write supply of I, GAMS understands that supply of Seattle, supply of San Diego, because we have 2 values. Similarly, demand of j, right. So, j is a set we have earlier defined. So, this will be demand of New York, demand of Chicago, demand of Topeka, right. So, these 3 are the name of the equations, and how many equations are there are also specified using indexing, right. So, if we write supply of j instead of supply of I, right, let us say we write supply of j, in this case it will have 3 constraints, supply will have 3 constraints, supply at New York, supply at Chicago and supply at Topeka. Now, we need to define the equations, right. So, here we define the equation. So, we have used the equation name cost. So, we are writing what is the equation cost. So, we write cost over here and then space 2 dots, right, and then we write whatever constraint we have over here. So, here we have this equation to be written. So, the equation is the variable z, this equal to E equal to means it is an equality constraint, right. So, that is why we have equal to E equal to over here. So, to write this expression, right, so we are going to sum something. So, let us say z is equal to E is equal to, right. So, we write sum, right, and we are going to sum something, right. So, we are going to sum with I as well as with j, right. So, sum of I comma j. So, sum of I comma j, then this is the index on which we want to sum, then we need to have a comma and then the expression, right. So, C of I comma j star x of I comma j, that is what is written over here, right, and we need to end the statement again with semicolon. Then we write the equation supply of I, right. So, supply of I, here we have a less than equal to constraint, right, and we have summation over here. So, what we have is summation, we are going to sum something and it is going to be over j, right. So, sum j comma the expression. So, the expression in this case happens only to be x of I comma j, right. So, this is expected to be less than equal to a of I, right. So, less than equal to constraint in GAMS is written as equal to L equal to a of I. We end it with a semicolon, right. So, this is the equation for supply. Similarly, demand of j, we are going to sum it over I, right, because here we have summation over I comma x of I comma j, right, is equal to g, because we have greater than or equal to over here, right. So, equal to g equal to indicates that the left hand side has to be greater than or equal to the right hand side, is equal to g equal to b of j, right. So, we have defined all the 3 constraints, right. So, a good thing over here is, unlike MATLAB where we were forced to give all the constraint as less than equal to form, right, here we can give less than equal to constraint as well as greater than equal to constraint directly. We do not need to transform these constraints into this type, right, which was the case in MATLAB. If it is a equality constraint, we directly use equal to E equal to, if it is less than equal to, we use equal to L equal to, if it is a greater than equal to constraint, we use equal to G equal to, right. So, now we have defined all the constraints, right. Now, we are building a model, right. We use the keyword model, the name of the model. So, here we choose to give the name transport, right, and within this slash we give all. So, all is again a keyword. So, that means all the constraints which have been defined in the current GAMS file, right, are part of the model transport. Right. So, for example, if we do not want to have demand constraint, one way is to remove this or comment it, right. The other way is to build a model transport one, let us say, without including the demand constraint. We will see that a little bit later. So, for the current case, we are building a model, right. The name of the model is transport, and we are including all the constraints which have been defined in the current GAMS file, right. So, building model does not solve it, we need to explicitly solve using this keyword solve, right. So, we want to solve the name of the model, using has to be provided, right, and then the type of the problem. In this case, if we see, this problem is a linear programming problem. So, we provide LP and we want to minimize the objective, right. So, we explicitly say minimizing, and then we say the variable z, because that is what we want to minimize, right. So, if we have a maximization problem, then instead of this minimizing over here, we just need to give maximizing, right. So, again, unlike MATLAB wherein you are forced to solve only minimization problem, here you can solve a maximization problem as well as minimization problem without necessarily transforming the maximization problem into a minimization problem. So, this completes the description of the GAMS file. So, this has to be returned as a GAMS file, and if we execute this particular file, we will be able to solve the transport problem. So, now let us quickly go through the file once again, right. So, initially we define what are the sets which are there and then assign the values. Then we have this data. In this case, data is given as parameters, tables as well as scalar. So, over here it is declaration of the data. We are just declaring that there is a variable a, b, d, f and c, right, and then here we are providing the values for the parameters, and then over here we are defining the variables. We are declaring the variable x and z along with its description. Here we are assigning the type of variable, right. So, positive space variables x ensures that x will take only values which are greater than or equal to 0. Then we have the equations block. So, we first write the keyword equations and then list the set of equations. Then we have the equations block. We declare the equations and their appropriate description, and then we define the equations. This is followed by building the model, right. Here the name of the model is transport and it includes all the constraints listed in this GAM file. Model is a keyword. In the next line we have solve, which is a keyword. So, we are solving the model transport using linear programming with minimization of z. So, the statement all which we had previously basically means cost comma supply comma demand, because those are the three constraints. So, for example, if we do not have demand constraint, then we can remove this comma and the demand, right. So, in this case, though the equation demand has been defined and assigned, right, it will not, the model transport will not contain the demand equation, it will only contain the equation related to cost and supply. So, here we can list out 100 equations, and depending upon what we are solving, we can include a selected set of equations and can build multiple models in the same file. So, when we execute that GAMS file, right, this is the output that we would get, right. So, basically we will get two types of file, one is called as list file and another one is called as process log file, right. So, list file will contain two parts. So, on the left hand side we get the contents of the list file. By clicking any of this, we can go to the appropriate section in the list file. So, the list file is usually a very long file. So, we can jump to the appropriate section. In this section, we can click on whatever is required. So, for example, if we want model statistics or solution report, we can directly click on that and we will be able to see that particular section in the list file. So, now let us look into the list file. So, the first section of list file has this echo prints, right. So, this is an example of list file for the model which we have built, right. So, this is our GAMS model. When we execute, we get a list file. The first section is the echo prints. So, over echo prints, if you see, it is an exact replication of the model that we have, that is why it is called as echo, right. So, if you want, you can switch it off, but by default it is on, right. So, once we save the list file, at any point of time we will also be able to know what is the model which we solved for the results in the list file. So, this is a big advantage of list file, unlike many other software in which results are usually stored away from the program which generated it. In GAMS, as part of list file, we will get both the model as well as the results in the list file. So, list file also has this equation listing, right. So, this is our model. this is the equation listing, right. We have these three equation, cost, supply and demand. So over here the equations are listed, that is why it is called as equation listing. So what we wrote over here, cost is Z is equal to E is equal to sum of I comma j comma Cij into Xij, what we have written over here. So the expanded version of this is given over here. So Cij, if you calculate, it would come to 0.225. Then the variable x, which indicates Seattle to New York, Seattle to Chicago, Seattle to Topeka, San Diego, New York, San Diego, Chicago and San Diego, Topeka, right. So that is what is over here. So what is displayed is Z minus this part equal to 0, right. So that is why we have Z over here, which is positive, and the rest of the terms have a negative sign, right, and the right hand side is equal to 0. So this is the cost equation. Let us look at the supply equation, right. So we have supply is over set I, right, and I contains two values, Seattle and San Diego. So here we have supply of Seattle and supply of San Diego. This constraint is actually a less than equal to constraint, right. So that is why we have less than equal to 350 and less than equal to 600, right, and the variable, if you see, it is summed over j, right, and j is our market, right. So supply of Seattle is nothing but x that is going from Seattle to New York, x that is going from Seattle to Chicago and x that is going from Seattle to Topeka. So that has to be less than equal to 350. So similar to supply Seattle, we also have supply San Diego, right. Then the third set of equation is demand. Demand runs over j, right, and j we have three values in demand. So demand of New York, demand of Chicago and demand of Topeka. So over here this equation is sum over I x of I comma j, right. So since this is the j, this remains constant. So whatever that is coming from Seattle and whatever that is coming from San Diego to New York should be greater than or equal to 325. Similarly for Chicago, whatever is coming from Seattle and whatever is coming from San Diego has to be greater than or equal to 300, and the third constraint, right. So we do not need to explicitly specify these equations when we were writing model. Model we wrote in a very compact way, right, similar to what we would develop using a pen and paper. That is the advantage of GAMS, that the model which we develop in algebraic form can almost be directly coded into GAMS. So since in this problem we did not give default values, so the default values of all these 6 variables, so there are 6 variables because x is defined across I comma j and I is 2 and j is 3. So basically we have 6 variables. So since all the 6 variables are positive and we have not given any initial guess, right. So by default takes value of 0 for all the decision variable if we do not supply a initial value, right. So if a value of 0 is taken, the left hand side will come out to be 0. So that is why we have LHS is equal to 0, and since 0 is equal to 0, this constraint is satisfied. So it does not indicate that there are any infeasibilities, right. Similarly these two equations also, if you see the value 0 over here, right, then all of this would be 0, the left hand side is 0 and the right hand side is 350. So 0 is less than equal to 350 is what we currently have because the initial values are taken to be 0. So this constraint is satisfied. Similarly this constraint would also be satisfied. However, if you look at into these 3 constraints, right, so here if we take 0 0, the left hand side is 0 but the right hand side is 325 and this is a greater than equal to constraint, right. So 0 is greater than or equal to 325, that is the current state. Since we have not supplied any initial value, GAMS takes it to be 0. So in this case we have LHS to be 0, greater than equal to constraint and 325. This is what indicates that we have infeasibility over here. So in all the 3 cases, the left hand side, if you see, it will come out to be 0 and the right hand side is a positive number and the constraints are of greater than equal to, right. So all these 3 constraints at the initial point which is 0 0 0 is an infeasible point, right. So this equation listing does not give you the result, this equation listing tells us what is in the initial phase. So, we have seen two components of list file. The first one was ecoprint, right, which is just reproducing the model, and then the equation listing, right. The other part of list file is model statistics. So, model statistics tells us about the equations and variable. So, here if we see, we have two types of variables, right. So, that is what is blocks of variable. So, we have two types of variable. So, one is indicated by x and the other one is indicated by z, and we have three blocks of equations, right. One is cost, another one is supply of I, and the other one is demand of j. But the number of decision variable is x. If we see, it is just not one single variable, but it is I comma j, right, x of I comma j. So, I in this current case we have two values and j we have three values. So, basically x of I comma j has 6 values, right, because there are 2 elements in I and 3 elements in j, right. So, 6 variables plus another variable, this is a single variable z. So, we basically have 7 variables. So, that is what is denoted here. And then over here if we see constraint, this is just one single constraint, supply of I is for Seattle as well as San Diego. So, here we have 2 constraints, and demand we have for 3 cities, right. So, this will be basically 6 equations, 3 plus 2 plus 1. So, that is what is given over here, 6 equations. Remember, this side is the GAMS model, right. So, we are just showing you the model so that it is easier to explain, but list file has only ecoprint, the model is separate, right. So, in status report we get the solution summary. So, the name of the model is transport because we solved the transport model, right. Type LP because we solved it as linear programming problem. The solver by default it took Simplex, we did not specify the solver. So, that is why it shows solver is Simplex. The objective is to minimize Z and the direction is minimize. So, we since it is a minimizing problem we got minimize over here. Had it been maximizing over here, we would have got maximize over here, right. So, over here it says the solver status and the model status, right. So, solver status 1 indicates normal completion and model status 1 indicates that it is the optimal solution, and over here it gives the objective function value. So, the value of z is 153.6750. So, this section shows the amount of time that is used. So, in this case it is 0.047 seconds and it employed 4 iterations, right. So, the default setting for time and the iteration count is 1000 and this value respectively. So, if you see that this value is also 1000, right. So, that means the amount of time utilized is also 1000 and the limit is also 1000, then it might happen that it is not normal completion, it completed because of lack of additional resources. Same thing for iteration. So, now we have seen 4 sections. One is ecoprint, equation listing, model statistic, status report, right. So, the decision variables are given in solution reports, right. So, the value for variable x can be found here. So, over here it enumerates the variable, right. So, for example, x I comma j, right. So, x I is Seattle. So, we will have x Seattle to New York, x Seattle to Chicago, x Seattle to Topeka, and the second value is San Diego, right. So, San Diego to New York, San Diego to Chicago and San Diego to Topeka, right. So, these are the 6 decision variables which we have. The value of the 7th decision variable we have seen, right, which was nothing but the objective function value. For this 6th variable, the lower bound which we had is zeros, right, because we have given it as positive variable. So, the lower bound is 0. The upper bound is infinity, again because it is a positive variable, we did not explicitly specify any upper bound, right. So, the lower bound is 0. Since it is 0, GAMS does not write 0, it just puts a dot. So, Seattle to New York we need to ship 50 cases, Seattle to Chicago we need to ship 300 cases. Nothing is being shipped from Seattle to Topeka because here it is a dot which basically indicates 0. So, from San Diego to New York 275 cases are to be shipped, from San Diego to Chicago nothing is being shipped, and from San Diego to Topeka we need to ship 275, right. So, this is how we get the values of the decision variables. So, being an introductory video over here, we are not dwelling into too much details. You can look into the help of GAMS and try to identify what are the other things that GAMS returns. For example, you can try to find out what is this marginal price and if it indicates the shadow prices. So, those are the major portions of list file, right. We will now look into the log file. This is an example of the log file. So, the log file gives the location of the GAMS file, the version with which we are solving and the license details, with what settings it was executed, the objective function value obtained in each iteration. So for example, here for the same problem, we did get 153.675 in the 4th iteration, right. So that was given by the list file, but what is happening at every iteration was not given in the list file, right. So that can be obtained from the log file. It also provides us with the time taken for completion, the reason for termination of the algorithm, and also the objective function value. So this is the GAMS IDE, right. So here if we go file new, this is where we can write the GAMS code, right. So this is the GAMS code which we have discussed. So this is also available over here in this GAMS model library. If you click on this sequence number, the first example that you would get is the GAMS model, right. So this is what we have copied over here, right. So if we now execute this, you can either click on F9 to execute it, or you can click on this button, right. So if you see here, what we get is the log file, right. So if we click on this open log, it will open log in the editor itself, right. So this is the editor, right. And then we have this listing file, untitled_2.gms is the file that we executed. The log file is untitled_2.log, right. So this basically gives the details which we have previously discussed, and this is the listing file. So the listing file, let me close this, right. So the listing file, as we had shown you earlier, has this left hand side which is more like an index, and the file itself is on the right hand side. This entire thing is the listing file. So over here we can go and click on anything. So for example, let's say we are not interested in analyzing the entire list file, we want to see only the values of the variable x. So we can double click on this and it will correspondingly show only that particular value. If you want to look at the equation listing, let's say you want to look only at the demand equations listing, so it directly goes over here, right. If you want cost, then double click on this. Similarly, the supply, if we double click on this, it will show the equation listing of the supply constraints. Over here we have the model statistics which we had discussed, and the solution report or the solve summary over here, right. So over here it directly specifies 4 iterations were utilized, right. The details of the iterations are available in this log file. So over here we also have this display statement, right. Display is the keyword, x.l and x.m, right. So when we specify this display x.l and x.m, it gives the final values of the decision variable L and also the marginal prices associated with x. We leave it to you to find out what are marginal values, right. So over here if we go to this display part, we will have x over here. So this is x.l, which are the values which we discussed, right, that nothing is shipped from Seattle to Topeka because it was 0, and nothing is being shipped from San Diego to Chicago. This part is being displayed only because of the display statement, and these are the marginal prices. So this example which we discussed was a linear programming problem, right. Now let us look into a mixed integer linear programming problem. For mixed integer linear programming problem, non-linear programming problem, mixed integer non-linear programming problem, much of the content remains the same except for the solve statement, in which we need to specify the appropriate category of the problem. So now let us look into a mixed integer linear programming. This is the example of a paint company which we had discussed previously, right. So we will not go into the problem. This is the profit. So our objective was to maximize the profit, and it has 2 decision variable x1 and x2. In this case both of them are integer variables, x1 and x2, right. So what we will do over here is we will define variables. So in this case we have 3 variables, x1, x2 and z. Z is also a variable. Remember, in GAMS we need to specify variable, right, and the objective function is to be equated to that variable, right. So that is why we have this z. Over here we have description for all the 3 variables, right, and then we specify integer variables as x1 and x2. So since we are listing x1 and x2 under this integer variable, it will be ensured that the values of x1 and x2 are integers. Over here we have 5 equations, but this is more like an upper bound. So we will not treat it as an equation, we will specify that the upper bound of variable x2 is 2. So basically we have 3 constraints, and since GAMS requires the objective function to be an equation, we have another equation over here. So basically we have 4. Under equations we define profit, raw material 1, raw material 2 and demand. These are just names for the constraints, right, and this is the corresponding description of those 4 constraints, right. Over here we specify the constraint. So profit dot dot, and then we said z is equal to E because this you can consider it to be an equality constraint. 5x1 plus 4x2 is an equality constraint, and then we are saying maximize z. Remember, E equal specifies a constraint, whereas if we just say z is equal to 5, that means we are assigning a value of 5 to z, or if we say z is equal to 5x1 plus 4x2, that would merely indicate that we are assigning the value of 5x1 plus 4x2 to be z, right. If it is a constraint, we need to give it in the form of equal to E equal to, and then we specify the other two constraints, right. So, over here it is 6x1 plus 4x2 should be less than equal to 24. So, 6 into x1 plus 4 into x2 is L equal to 24, equal to L equal to, because the constraint that we have is less than equal to. Similarly, the second constraint is x1 plus 2x2 is less than equal to 6. So, x1 plus 2x2 equal to L equal to 6, right. So, this is not 1, this is L. Similarly, we have this demand constraint. So, the demand constraint we rewrite as minus x1 plus x2 should be less than equal to 1. So, over here minus x1 plus x2 is less than equal to 1, and this upper bound we are not specifying it as an equation, right. So, if we want to specify an upper bound, we can use the name of the variable, in this case x2 dot up. So, up will help us to specify the upper bound. If we want to specify the lower bound, then we can do x1 dot lo is equal to 5. So, this will specify the lower bound for the variable x1. So, x1 cannot take a value lower than 5. So, in this case we are specifying x2 dot up is equal to 2. Remember, over here it is not equal to E equal to, because this is not a constraint that we are writing, right. Here we are just specifying that the upper bound is 2. So, we should not use equal to E equal to, we just say x2 dot up is equal to 2. Similarly, if the lower bound is 5, we just specify x1 dot lo equal to 5 and not x1 dot lo equal to E equal to 5. So, this is not to be done. So, over here we want to include all these 4 equations. So, between this slash operator we have this all, and we are constructing a model whose name is paint problem. Then we are solving the same model which we built in, solve paint problem using, right, not MILP but MIP, right. Remember, GAMS does not recognize MILP, it only recognizes MIP, but it basically refers to mixed integer linear programming, and in this case we want to maximize, right. So, the previous problem we had minimizing because we wanted to minimize the variable z over there. In this problem we want to maximize, right. So, over here maximizing, and then the variable, right, the variable z, because it indicates this equation, which is what is our objective function. So, over here if we want to solve the problem with demand constraint and without demand constraint and then compare the results, right. So, here then we can say model, right, let us say P1 is the name of the model. So, here we can give profit, because we want to include that equation, raw 1, raw 2, and that is it. We do not want to have this demand equation, and then we can have another statement, let us say solve P1 using MIP, because it will be a mixed integer linear programming problem, maximizing the variable z. So, now since we have two solve statement, we will get results with respect to both the models. Then we will be able to see the impact of this constraint on the profit. So, this is the GAMS model file for this problem, and this is a section of the list file for this GAMS model, right. So, the status report shows normal completion and optimal. The resource that is used is less than the maximum, right. And over here we have 4 blocks of equation, and the number of single equation is also 4, because we do not have any set on which these equations are running over, and we have only 3 blocks of variable, and each of the variable is actually a single variable over here. And over here we have 2 discrete variables, right, x1 and x2 are discrete variables. So, we have 2 over here. So, this section provides us with the solution. So, the lower bound for the integer variables are 0, and the upper bound based on the constraint is 102, right. For the second variable we had specified that upper bound is 2. For the first variable, the upper bound because of this equations comes down to 100. The final solution, the optimal solution, has a value of x1 is equal to 4 and x2 is equal to 0, right, with the objective function value of z is equal to 20, right. So, this is how we solve a mixed integer problem or mixed integer linear programming. So now we have seen how to solve a linear programming problem and a mixed integer linear programming problem. We will now look into how to solve a non-linear programming problem. Right. So this is an example of a non-linear programming problem. Right. So we want to minimize x1, right, subject to these constraints. So we have 6 variables x1, x2, x3, x4, x5 and x6. So for that problem we do not need to define any additional variable. Previously we were defining z is equal to the objective function. Here the variable x1 itself is an objective function. So basically what we can say is remove this and just say minimize x1, right. So in this case we have 6 variables. So we define x1, x2, x3, x4, x5, x6. We have equation 1, equation 2, equation 3, 4, 5 and 6, right. So we have 6 equations. Let us name those equations as R1, R2, R3, R4 and B1 and B2, right. So this is B1, this is B2, this is R1, R2, R3 and R4, right. So we are specifying the equation R1 dot dot space x1 into x2 equal to E equal to 1 because it is an equality constraint. Second equation R2 x3 into x4 divided by x1 is equal to 4.8, right, again equality constraint. R3 is x5 into x6 by x2 equal to E equal to, because these are equality constraint. The fourth equation x4 into x6 is E equal to 1, right, because of the equality constraint. Then equation B1, right, so x1 into 10 power minus 7. So here we write 1 E minus 7 into x3, again equality constraint. So we have equality E equality. On the right hand side we have x2 plus 10 power minus 5 x5. So x2 plus 10 power minus 5 x5, right. Similarly we have equation B2. So over here if you see, unlike in MATLAB wherein we were forced to provide the right hand side should be less than equal to 0 for nonlinear constraints, and for nonlinear equality it is of this form. So we had to transform the problem into this particular form. Here there is no need to do anything of that sort, right. So the right hand side can actually be an expression, it need not be a constant, right. And again in MATLAB we were restricted to solve with a minimization problem only. Here we do not have that problem. We can solve a maximization problem directly without transforming it into a minimization problem, right. So now we are constructing this model using the keyword model. So the name of the model is given as WALL, WALL, right, and we want to include all these 6 constraints over here, right. So slash all slash, right, and we ended with a semicolon, right. So this will construct a model known as WALL which will have all these 6 equations, right. And over in this case we also specify the initial starting point. So the starting point can be given as name of the variable x1 dot L. L means level, equal to whatever that value is, right. So again remember it is not x1 dot L equal to E equal to 1, right. So that is only for the constraint. This is not a constraint, this is just a starting point, right. So for all the 6 variables we are starting with a value of 1, right. So that starting point is given, and then we specify solve the model WALL using NLP, right, because this problem if we see there are no integer variables but there are nonlinear constraints. NLP minimizing because it is a minimization problem and we want to minimize the variable x1, right, and we end it with a semicolon, right. This model is also taken from the GAMS library, right. So if you look into this model WALL you will be able to get this code over there. So this is the solution for this model, right. So section of the list file is shown over here. We are not showing you the ecoprint or the equation listing, we are directly looking into the results, and we have normal completion, the solver status is normal completion, and the objective function value that we get is minus 1. So x1 is equal to minus 1, right, and the rest of the values can be obtained from here, right. In this case x1 was the objective, so this value actually corresponds to this x1, otherwise it just corresponds to the objective function value. Now we have seen a linear programming problem, non-linear programming problem, a mixed integer linear programming problem. Now we will look into a mixed integer non-linear programming problem. So this is the example that we will consider for mixed integer non-linear programming problem. Here we have a minimization problem and the variables x1 and x2 are integer variables and they have an upper bound of 200. The variable x3 has a lower bound of 0.001 and an upper bound of 200 and it is a continuous variable. and we have 3 constraints over here. All the 3 constraints are of this greater than or equal to nature. As discussed earlier, we do not need to transform it into less than equal to form. So, since we have 3 variables, first we are defining 3 variables which we already have in the problem, and we are defining another variable obj var, right. So, this is obj var is equal to this, and then we are saying minimize obj var. This is the name of the variable, right. Instead of z, we are using obj var. Again, this model is available as part of GAMS library. So, over here we have 2 variables which are integers, right. So, the first variable I1 and the second variable I2 are integers. So, I1 comma I2 and semicolon. Over here we have 3 equations, and as usual GAMS requires the objective function to be given as an equality constraint, right. So, we have 3 plus 1 4 equations. So, the 4 equations are given over here. So, this SQRT helps us to take this square root. So, this equal to g equal to is because the constraints that we have are of the type greater than or equal to, right. And over here we have the upper bounds for variable 1, 2 as well as the variable x3, right. So, what we have x1 and x2 over here, x1 has become I1, right, to indicate that it is an integer variable, x2 has become I2 to indicate it is an integer variable, and x3 what we have in the problem is maintained as such as x3. So, over here we specify the upper bounds of the 3 variables. For the variable x3, the lower bound is 0.001, right. So, that is why we have x3 dot LO. So, this LO stands for lower bound. Over here if you see, we have this star over here. So, when we begin a line with a star, it basically means it is a comment, right. So, here we are specifying the bounds of the variable, and in this case we have been given the initial value. So, we specify I1 dot L is equal to 1, I2 dot L is equal to 1, x3 dot L is equal to 1. Again remember, not equal to E equal to, these are not constraints, this is just a starting point. Again for bounds, we are not supposed to give it in terms of equality constraint. So, we are constructing this model whose name is M, and we want to include all the equations specified in this file. So, we have model M slash all slash semicolon, and then over here we are solving using the keyword solve. We are solving the model M using MINLP, right. So, this is again a keyword. So, the keywords which we have seen is LP, NLP, MIP and MINLP, right. When we say MIP, it is actually MILP, right, but if you write MILP you will get an error, you will have to write MIP. So, that you will have to be careful. Depending upon the problem that we have at hand, we will have to use one of these. And over here we want to minimize this objective function, right. So, minimizing obj var, because that is the variable which is defining the objective function, right. So, over here if you see, obj var is over here, right. So, what has been done over here is obj var is equal to whatever here we have, right, and then it has been taken to the left hand side. So, that is why we have this 4th equation. So, this basically corresponds to the objective function. So, we could have also written this as, instead of this we could have just written obj var equal to E equal to and this expression whatever is given to us. So, we could have also done, or we could bring it to the other side and give it as a equal to E equal to 0. So, the solution of this GAMS model is given over here. So, the interpretation is similar. The number of discrete variables, the number of equations and variable, blocks of equations, blocks of variables. Over here we have the solver status, which is 1 normal completion. The model status is 8 integer solution. This basically means that the solution which has been reported by GAMS is an integer solution, because we have some variables which are integers. This gives the amount of time and the number of iterations it took to complete this problem, right, and this is the objective function value, right. So, over here values of the decision variables are given. So, this is the lower bounds, these are the upper bounds which we had specified over here as 200, and these are the values which have been determined by the solver DICOPT, right, and the problem that we solved is MINLP, right. So, here the decision variables are I1 is equal to 4, I2 is equal to 3 and x3 is equal to 0.631, right. So, the problem required I1 and I2 to be integer, and over here we get integer values for that. So, this is how GAMS can be used to solve linear programming, non-linear programming, mixed integer linear programming and mixed integer non-linear programming problems, right. Unlike MATLAB, which was not able to solve mixed integer non-linear programming problems which involved equality constraint, GAMS can solve those type of MINLP problems also. So, with that we will conclude this session. Thank you.